This is a recording of the second part of Lecture 2 with the last 7 or 8 slides that we have not had time to cover in the normal lecture slot. And I'm offering this recording because the next tutorial, the one on Friday, will actually cover material that in fact comes in these slides. So the second part, or the last part of our lecture, was on assembly languages. All right, so what are they? So imagine that in the beginning, when they were invented, that was in the 50s, they were thought as a means of making machine languages more readable. Machine languages are sequences of numbers, right? So it's very difficult to remember, for instance, that the hex number D3, for instance, performs addition, and the hex number C9 performs return from a procedure, right? So then people assign mnemonics, which are abbreviations of words, to these numbers to make them easier to remember. And this led to what was called later assembly languages. There's a one-to-one mapping between machine instructions and assembly languages instructions. So the execution unit is an instruction which performs a very limited amount of computation. There's no means of structured programming. We do not have loops. All we have is branching instructions and yes, branching instructions, right? Conditional or unconditional. That's the only way to perform repetitive computation. Programs are large in terms of lines of code, but every line of code will only take a few bytes of machine code. So, like 20,000 lines assembly language program, which by means of programming effort would be very large, in fact would produce only 50 to 60 K of code, which by means of today's executable sizes is very small. They're different from every architecture. So the Pentium assembly language is different from the MIPS assembly language. And what we want to learn in this module is not a specific assembly language, but rather the skill of programming. To understand the level of skill, we don't even want to create the skill. We want to understand about how difficult it is as compared to higher level programming languages, how difficult it is to program, right? We want to be able to appreciate that. All right. So we're interested in low-level programming skill, but not really interested in a specific architecture. All right, so what we define is what we're going to call a vanilla assembly language, right? It's not really an assembly language, it is a restricted C. So imagine that in your C programs, you're only allowed to use 6 global variables. That's all. And these 6 global variables are given, right? EAX, EBX, ECX, EDX, ESI, and EDI. And I'm using these names because these are the names of the Pentium registers. So I want to create a bit of similarity with the Pentium. There is one global array, which is of type unsigned char. So it can be larger, right? Memories are, this represents the memory, and memories are much larger by today's standards. But you're not allowed to declare any local variables. There's only one function with this prototype, right here. This is the only function that you're allowed to write. And your code has to perform any computation, like any functions in any other programming language. So we'll see how, right? So these variables simulate registers. The array simulates memory. And the exec is just a placeholder folder for code, right? Just because we need to comply with C syntax. Now, what kind of code can you write inside your exec function? Well, there's the following operands. So remember, these are limitations that we are placing on the C language to make it similar in programming effort to an assembly language, right? So these are the only variables that you can use, right? This is all you can declare as storage. Variables and array, right? No other array, no other local variable, no other global variable. Only one function which must have this prototype. No other functions are allowed. So in order to define the instructions, we're going to define first the operands. What operands can appear in those instructions? So obviously we can have any of the 6 global variables, right? And this is one type of operand, global variable. There's an index expression that we're using here, right? So these expressions will be allowed to be used as indices. So it's either a global variable, right, one of the 6 here, or a constant. Any kind of integer constant is allowed, right? Or is global variable plus constant or global variable minus constant, right? These are all the expressions that are allowed. For instance, EAX plus 3 is a legal index expression. EAX plus EBX is not. 3 times EBX is not, right? So this is not allowed, this is not allowed, right? Only global variable plus constant, global variable minus constant. Now, other kinds of operands, right? What kind of memory elements? So, you can index the memory by some index expression. Any legal index expression can appear within brackets. And of course, this will be of type char. What if you want to store integers or unsigned integers or shorts or unsigned shorts? What if you want to do that with a memory? Well, we convert. So this is a conversion. These are legal operands. You can put an index expression. And this, for instance, this expression will access 4 bytes, 4 characters in our array. Right? So that's because memory for the Pentium system is a byte indexed array. It's one byte after another. It's an array of bytes. But whenever we store, so to store an integer, we need 4 bytes, so we're going to use 4 consecutive bytes, right? So if I want to store an integer in memory, I'm going to use array elements, maybe, possibly, 0, 1, 2, 3. I need to use 4 of them. Or if I put it at some arbitrary address A, I'm going to use A plus 1, A plus 2, A plus 3, right? So I need 4 bytes. To access 4 bytes in an array of type character, right, unsigned character, I need to perform this conversion. Similar conversions will be required if we want to operate with unsigned integers or with 2-byte integers or with unsigned 2-byte integers. All right, these two will be very infrequent. So we have a few examples here. Right? So, all right, let's do the animation. We simulated Pentium operands. We have a few examples here. Remember, for instance, that A within quotes is a constant, and the address of a label is also a constant. Right? The conversion is necessary because the array is byte accessible. So whenever we need 4 bytes, we need to convert. All right, so these are a few examples. We have register operand. We have integer in memory for 4 bytes of memory, right? Starting at the address indexed by register ESI, right? An unsigned short, so this is 2 bytes. 1 character, right? Unsigned int in memory, 4 bytes, right? And these are not allowed. These are not legal expressions. All right, for code, we allow only very simple assignments of 2 operands, or the shortcut assignment between 2 operands, right? So these are all the ones that we allow, right? Operand is assigned operand, operand plus equal operand, operand minus equal operand, operand star equal operand, and all the other ones, right? Shift equal, percent equal, division equal, all the other ones, and equal or equal, that are performed only between 2 operands are allowed. Okay, so these are examples of correct assignments, right? EAX equals EBX, EAX shift left memory operand, EAX equals MEBX. Right, so you can assign, even though this is an integer, you can assign less. And so on, right? So we can place an integer in memory. We can add some address, right? We can place an integer, right? 10 in memory. We can add the digit 0 to a memory element. These are illegal, right? So as soon as we have 3 addresses, we get illegal instructions. So again, this is a restriction. Only a limited types of assignments are allowed. Go-to instructions are allowed, both kinds, right? Fixed label and computed go-to, and this must be an operand, right? And we can go to a computed operand. Remember, like most likely, these will be array elements containing addresses of labels. Boolean expressions. All the Boolean expressions are allowed, but we don't allow 2 memory operands in the same expression. Not here, and actually not here either, right? No 2 memory references in the same expression, right? So we were saying that this is illegal. We allow only one kind, a very simple kind of if statements. If Boolean expression, go to, label, or operand, right? So here we can have either a fixed go to or a computed go to, right? But we can't put an arbitrary number of instructions in here, right? We only allow go to. That's the only thing we allow here. All right. So let's look at an example. We take the original function that we have discussed. All right, and we translate it into vol code, right? So let's see how the translation progresses. So first of all, how do we transfer the arguments? That's a matter of convention, right? Whenever you write, you have to make the assumption that the arguments will be placed in certain registers, typically, and you have to say what they are. It's up to you, but you have to say what they are, right? So here, we make the assumption that arguments A and B would be placed in registers ECX and EDX. And we also have to know how we return the result. So here we make the assumption that we return the value in EAX at the end of the function. So as soon as we reach the end of the function, we expect that the register EAX contains the result. Okay? So, all right. So you see, because we return S here, we're going to try to simulate the variable S with the register EAX. And we're going to try to simulate the variable CNT with the register EBX. Notice that in here, in the function, we do not define any local variables. The variables that have been defined in here, in power, right, will have equivalents, but those variables cannot be local variables. So if b less than 0 returns 0, it returns 0, will be converted into, so what I was just saying, that these two local variables will be converted into the corresponding assignments on the right. Okay, so now if b less than 0, we cannot return 0 immediately, because the only thing we can write in an if here is a goto instruction. So I'm going to say if edx is less than 0, right? So edx is the equivalent of b, right? We go to some place where we can perform the return, the equivalent of return. So what do we do here, right? This will be the label, return 0, and we load the return register with the corresponding return value, right? So this return value will be placed in the return register. Next, we have, we're going to have the loop, all right? And inside the loop, there's an if statement. So it's a good thing to start from small towards the outside, right? So what do we need to do here? Well, again, if is restricted because it forces us to use a goto statement, right? So the first thing that we need to do is we have to translate this expression, right? And this expression can no longer be performed in one step, right? We need two steps because we do not want to destroy the value of b. So what we do is we save edx, which is the equivalent of b, into edi, and then we conjoin edi bitwise with the result of 1 shifted to the left by 30, right? So this is equal to this. Okay? So at the end of this instruction, edi contains the result of the Boolean test. And we have not destroyed the value of edi. So now we can check the value of the test, and if it is non-zero, we have to go to somewhere where we can execute the code equivalent to the then branch. Otherwise, we shall continue with the code equivalent to the else branch. So this is going to be the else branch, and this is going to be the then branch, right? So let's see that. We can see that the then branch goes there, because whenever this is non-zero, we jump, right? We jump to the then branch, we jump here. So then the pink code will be the then branch. Let's see what happens in there. Well, again, this is something that has too many operations, so we have to convert it into a sequence of instructions. So we're going to perform EAX star equal EAX. So this is S equals S square. And then the result of that we multiply further by A, which is ECX, right? So after this instruction, right, S corresponds, S contains the correct value. We have to do the same here. So you see this value in C is in fact this constant. And again, we need two operations, right? We take EDX and we conjoin it bitwise. We perform a bitwise conjunction with this value, and that gives us the partial result of this expression. And then we further shift left by 1. So this guy corresponds to this operation. So this will be the translation of the then branch. And up here is going to be the translation of the else branch. So it's quite clear now, right, that S star equal S is going to be EAX star equal EAX, and B left shift by 1 bit will be EDX left shift by 1 bit, right? So we know how we translate each of these parts. Let's see how we translate the while loop. The while loop is the green part, so it's a skeleton there. How do we do that? Well, we have to compute this expression, right? So remember, EBX is in, CNT is simulated by EBX, so we decrement, right? And this needs to be the negation of this test. If the negation is true, then we don't have to execute the loop at all. So we go directly to the return. S already has the value. EAX already has the value that we want, so it's a correct return value. Otherwise, we go into the if test, which is this part, right? This part. This part up to here, and we execute the if test, right? And at the end of the if test, we hit this go to instruction, which takes us back to the top of the loop, where the expression is again evaluated. And then if the expression is not true, right, if the negation is true, which means the expression is not true, we jump out of the loop. So the jump is right here, where the function returns with the correct value in the register EAX. So this is a simple example where we take a full-fledged C function and we convert it into this restricted dialect of C, which we call vanilla assembly language. Notice that the memory has not been used so far. We will see plenty of examples where we use the memory, but we just want to start with a simple example. Okay, and hopefully this is straightforward, and it emphasizes something else. It emphasizes that there is a systematic translation principle at work. Notice the colors, right? Each type of statement on the left can be seen as a skeleton that translates into another skeleton on the right. All right. So inside the if, right, the pink blob and the blue blob are placeholders for code inside the if statement, right? So you can see that the yellow skeleton on the right has similar holes for holding the translation of the then branch and the translation of the else branch, right? So the translation of the if will have two placeholders for the translation of the else branch and the translation of the then branch. So this is pretty much how it will work. Translation is a recursive endeavor, right? We go hierarchically from outermost statements, right? We translate the skeleton and we translate then hierarchically the nested statements. So we can test the code, right? So how do we test the code? Well, here we just want to find out whether the code works correctly. So we can write any main function we want, right? Anything here is allowed, right? But we want to test whether exec works. So we load the registers, call exec, print result. Load, call exec, print result. Right? So this is testing code. It's not really part of your answer. Even if in an exam question, if you are asked to translate from power to val, all you need to give me is this. The main is not part of the answer, right? But, of course, when you solve your homework, you will want to find out whether your code works. And when I mark, it will be easier if you provide me with your main function so I can verify that your code works correctly, right? And in your main function, you can write any kind of code that exhaustively tests your exec. Just remember, don't put stuff that is supposed to be, that comes from the power function outside of the exec, because then it will not be a correct answer. Okay, so this is what the code does. Set up arguments, perform computation, print results. Okay? So remember, don't try to cheat by putting stuff related to the computation inside the outside of the exec. All right. Finally, so what have we learned in this lecture? Remember, all software executes in the assembly language code. So we would like to understand what kind of assembly language code is executed from any language that you write your programs in, right? To understand issues related to efficiency, time efficiency, memory efficiency. C was devised as a portable assembly language, so keep that in mind, right? It's supposed to help you learn or write as little assembly language as possible for embedded code, for operating systems, for system software in general, right? C was not devised as a high-level application development language, even though it was used for that purpose extensively. And then there is much criticism coming from that area about C. C is very bug-prone. Sometimes it's seen as cryptic code, not very readable, and so on. Well, those who invented it were very happy with it, right, for the purpose for which it was invented. Every language is a tool, and a tool has to be used for the right purpose. All right, so we want to understand the relationship of C to assembly language as well as to other C languages, C included, and we will explore that relationship with the aid of translation schemes. So we're going to be using this vanilla assembly language in quite a few lectures, and especially when we explain how procedures work. Okay, this is it for today. Remember, this part of the lecture will be used in Friday's tutorial.